Hello, I'm Dikshant. I'll show you the features of our VIP and demo of few test cases as well. We will show here how our VIP will help in verification. So let's begin with the webinar, which has useful and interesting information. Let's start with USB4 VIP overview. TrueChip USB4 VIP is fully compliant with standard USB4 specification, as USB4 performs tunneling of USB3, PCI, and DP, so it is also compliant with their respective specifications. It is also backward compatible to USB 2.0. The USB 4 port contains a Type-C connection, thereby it also supports Thunderbolt 3 interoperability, USB Type-C, and power delivery specification. TrueChip USB4 test suite is fully compliant with latest CTS version, that is 0.9.8.0. VIP is easy to be plugged in a SoC, or DUT or IP can be modeled inside a VIP test bench. VIP environment can be configured in a domain with selected number of routers at each depth, which can be either hub device router or peripheral device router. It can also be configured for inter-domain as well. It supports all USB4 blocks, which are lane adapters, control adapters, TMU block, protocol adapters, etc. These blocks are configurable and controllable by the user to test error scenarios and to maximize coverage. It supports the modeling of USB4 dock, that is USB 3 or 2 data transfer to the USB 3 devices or 2 devices connected directly to USB 3.2 hub present inside USB 4 hub using PCI tunneling and XSCI controller in Thunderbolt 3 mode. VIP supports all possible speeds on the bus starting from 10 GT per second, that is Gen 2 single lane, and can go up to 40 GT per second, that is Gen 3 with lane bonding enabled. It supports time synchronization protocol over inter-domain and intra-domain with STLP mode, which can be enabled or disabled. We will see USB4 verification IP block diagram. TrueChip USB4 VIP consists of 5 modules: compliance test suite, verification engine consists of host, device model, monitor, and a scoreboard. Compliance test suite consists of standard test cases and sequences. Those are fed into the verification engine, which consists of host BFM. The sequences runs over the connection manager, which manages all the layers, lane adapters, and routers in the environment. The connection manager prompts the configuration layer through host interface adapter layer to generate the control packets, which transfer through the transport layer to the physical layer that consists of logical layer and an electrical layer. These logical layer and electrical layer are connected with pipe interface. The USB4 traffic then travels through the downstream facing port of USB4 by USB Type-C cable to the upstream facing port of the device model. The device router electrical layer collects the packet and passes them to the logical layer. Then the packets traverses to the configuration layer by the transport layer. The transactions from the native protocols like DP, PCI, USB 3 are done using protocol adapters, which tunnels their respective traffic and is connected to the transport layer. In between the bus interface, which is the USB Type-C cable, the monitor checker samples the packet, it decodes each packet and bifurcates them layer-wise so that each packet can be monitored distinguishably. Our scoreboard samples the packet from individual layer and from the monitor of each layer, then it traces and checks the integrity of the packet throughout the topology. Look at the USB4 verification IP blocks. The USB4 verification IP connection manager is fully compliant with the USB4 connection manager specification version 1.0. The connection manager is a part of USB4 host entity that discovers, manages, and configures connected USB4 devices. It is the role of the connection manager to enumerate all the connected device routers. It also performs router detection using the hot plug and unplug events. Setup down and tear down of paths is also performed by the connection manager. It also supports for the bandwidth allocation and bandwidth management among the enumerated routers. It also performs external features like enabling the lane bonding or enabling disabling of a TMU mode or performing downstream port reset. It also supports host-to-host tunneling, that is known as intradomain. It also supports logical layer level tasks, that is low power state entry exit, lane disable enable, or sleep wake management for lane adapters. Logical layer forms the link between the two routers in USB4. Logical layer handles the transport layer packets which are transferred using a byte streaming interface from or to transport layer. Logical layer is responsible for 128 132-bit or 64 66-bit encoding decoding, dual lane link setup, skew management, scrambling descrambling of the data, RSFSC encoding, pre-coding insertion and removal mechanisms. These can be controlled and configured by the user. It does the tasks for USB4 link management, error detection and recovery mechanism, power management, etc. USB4 link is accompanied by a sideband channel which is responsible for mechanisms for configuring parameters for the USB4 link, TXFFE parameters handshake, and retimer interaction. It also performs few features like sleep wake and disconnect, etc. The physical layer BFM is shown here where the logical layer and physical layer interacts using a pipe interface which is compliant to Pipe Interface Specification 6.1. It supports 10-bit, 20-bit and 40-bit parallel interface to transmit and receive USB4 data. It also has a reliable LFPS detection and transmission mechanism. This layer drives the data over the Type-C interface connecting the USB4 routers on the following speeds: 10 GT per second, 20 GT per second, and different speeds for Thunderbolt 3 serial data transmission rate. It won't be incorrect to say that the transport layer of a USB4 is the backbone of it, as it holds all the various other layers together. TrueChip's designed transport layer provides the very essential services like paths and routing of the tunnel traffic within proper credit tracking mechanism. Various buffer schemes are also implemented with types of flow control, link management, which are some of the core features that make a USB4 work the way it should. It has the transport layer packet format with HEC and SEC, ECC for maintaining header and data integrity. It supports all the standard timers and user controlled linear scaling factors for fast simulation is also supported. It also has bandwidth arbitration and priority schedulers for proper transmission of the data from various adapters. USB4 provides time synchronization among the local clocks of all the connected routers in both intra-domain and inter-domain setup using a handshake mechanism with the help of TMU block. The host router time is taken as the reference time for the entire domain, while all other routers follow it and synchronize to it. Time synchronization protocol explains certain timing parameters such as time offsets, frequency offsets, which are to be calculated periodically by each router. For these calculations, timestamps are noted by slave on reception of TSNOS packet from master, followed by a follow-up packet, a delay request response, a delay response message. Timing intervals between calculations depending upon the mode selected for TMU, which can be either high-fi or low-res. Further, the TSNOS exchange method can be of two types, bidirectional and unidirectional. This time sync provision helps tunnel protocols by isochronous timestamp packets correction in USB 3, precision time management messages in PCI, and link clock restoration in DP. Configuration layer basically is responsible for managing the router states and handling the control packets. These control packets within the domain are used to access all the possible configuration spaces of a router. Configuration layer also generates the response with respect to the request received. Connection manager can perform possible router operations and port operations with the help of configuration layer. Configuration layer is also responsible for discovery of the router happens when another router is hot plug. Then the connected routers gets enumerated by assigning it a topology ID by the connection manager. Using read and write requests, we can perform various things like enabling the lane bonding, downstream port reset in the configuration spaces. And then finally, notification to the connection manager in case when on some event routers needs to notify the connection manager, it will send a notification packet with event codes. For example, error when router is already enumerated or a link error has been occurred or any field in the read or write request is incorrect. Each host router shall implement a host interface adapter layer using descriptor rings, which can be transmit rings or receive rings for control packet flow and host-to-host tunneling. Descriptor rings are circular set of descriptors containing control feeds and pointer to data buffers in the memory. A descriptor rings can operate in two modes, raw mode and frame mode. It provides parallel communication channels for control packet transmission and host-to-host tunneling. It also provides end-to-end credit waste flow control mechanism to prevent overflow of received descriptor ring in case of host-to-host tunneling. It can support configurable, it can be configured for maximum supported task total paths, ring size, and data buffer size as per the USB4 specification. This layer, the protocol adapter layer, is responsible to communicate with the native protocols and helps to tunnel the traffic over the USB4 fabric. Each router can have multiple protocol adapters with respect to USB3, PCI or DP. As you can see in this image, these protocol adapters communicate with the bottom layers of USB4, which is transport layer and logical layer. TrueChip VIP supports two communicating mechanisms between this native protocol and the protocol adapter. One can be seen here as the pipe interface, and one can be implementation of their respective physical interface or the bus interface as well. This is the diagram for USB 3 adapter layer. Here the internal USB 3, which can be a host or a device, is connected over the USB 3 adapter layer, which is connected to the transport layer using TLM ports. The USB 3 protocol adapter tunnels the USB 3 traffic coming from the internal USB 3 device and sends it to the transport layer in transport layer packet format using TLM ports. Similarly, any traffic received from the transport layer is communicated back to the internal USB 3 device over pipe interface. It helps in performing receiver detection, training in polling state, or transferring data in U0 state. Other LTSSM states like recovery, low power states like U2, U3 are also covered here. It supports bandwidth negotiation, path setup, and tear down mechanisms as well. This is the PCI adapter layer. In this figure, the PCI controller, that is the root complex, and the PCI function, that is the endpoint on the other side, is connected to the PCI upstream and PCI downstream protocol adapter, which tunnels the PCI traffic. They are connected over the PCI link as shown on the figure. This link can be a pipe interface or the standard physical interface. PCI protocol adapter encapsulates the TLP, DLLP, and ordered sets. It supports the functionality shown on the screen, which are support for low power, pre-reset activation, deactivation, LTR capability, P2P egress control, etc. It supports all the possible lanes on PCI internal port starting from cross 1 to cross 32. Next is the DP adapter layer. There is a DP source and DP sinks, which can be LTTPR and non-LTTPR. These are connected over DP link to the USB4 protocol adapters. There can be multiple DP in adapters and DP out adapters in host or hub and can be multiple DP out adapters in a device. This layer is fully compliant with DisplayPort 1.4a specification. The protocol adapters are capable of supporting all three modes. It supports the paths possible for aux and main link, capable of plug, replug, and unplug event detection. It protects the main link path data with ECC and aux data with CRC32. SST and MST tunneling is also supported with configurable options of FEC and HDCP. This is the TrueChip's USB4 hub block diagram, which is shown in the figure on screen. There can be multiple USB4 hubs, which can be connected to multiple device routers or retimers as well. Currently, USB4 hub here is connected to a host router and a device router. USB4 hub contains logical layer, that is lane adapters at the upstream port and the downstream port, which is then connected to transport layer that receives and transmits transport layer packets. It also has a configuration layer, a TMU block, and also an interdomain block to support interdomain functionality. It is capable of performing all three types of tunneling, that is PCI, DP, and USB3, for which different protocol adapters are present. There can be multiple PCI, DP out, and USB3 downstream adapters. Here, The USB 3.2 hub and USB 2 hub supports their own respective control transfers like get port status, setup depth, etc. and interrupt endpoint. In this design, as you can see, the USB 3 data can be transferred to the internal USB 3.2 hub via USB 3 upstream and downstream adapters using USB 3 tunneling. In the second scenario, when Thunderbolt mode is enabled, the XSI controller and PCI endpoint components are generated that receives the sequence data from the XSI driver in USB4 host via the PCI tunneling. Here, the USB 3.2 hub do not receive the data via protocol adapters, but from the USB 3 host. Also, the USB 2 hub receives the data from the USB 2 host. These hosts are connected to the XSCI controller. Here, this is the functionality of a USB 4 dock, where external USB 3 or 2 devices can be directly connected. The USB 4 monitors and scoreboard is also present, the respective links from the hub that fetches the data and applies protocol related checks. Scoreboard here maintains the data integrity and also checks whether hub has successfully transferred the packet to the destination router if not to be consumed. These are the features listed which TrueChip's USB 4 hub supports. For example, low power states of USB 3 or operation at 20 GT per second single lane and dual lane. Figure on screen shows the TrueChip USB4 retimer block diagram where the USB4 retimer is connected to USB4 host router and a USB4 device router. There can be multiple onboard or cable retimers along the channel. The USB4 retimer contains a Thunderbolt block to support the Thunderbolt interoperability. It has a retimer state machine which governs the functionality of the retimer and a sideband register space. TrueChip USB4 VIP also has monitors specific to check retimer functionality and a scoreboard as well. The retimer participates in lane initialization process starting from phase 2 to phase 5 when TBT3 is not enabled or phase 1 to phase 5 when TBT3 is enabled. Number of retimers in a channel is notified by updating indexes in a broadcast RT transaction. Sideband transactions are used to access the SB register space. It supports the retimer state machines, CLD bit lock, forwarding, low power, and disconnect mechanism as well. Port operations can also be performed on the retimer. The figure shows an inter-domain environment in which downstream port of a router is connected to a downstream port of another router in a different domain. This is used to establish host-to-host tunneling. The USB4 connection manager supports the Ethernet over USB4 domain interdomain protocol, also known as USB4 net. This enables two USB4 PCs to establish a USB4 net connection. The interdomain is discovered by the connection manager when a connected router found to be already enumerated in its other domain. As the connection manager detects the interdomain link by exchanging UUIDs, which is unique for every domain, it also exchanges the interdomain property blocks. The link state change requests can also be shared if lane bonding is enabled, and time sync operation can be performed if enabled by the user. After this, path setup for host-to-host tunneling will be done, where the login request and the logout requests can be shared. Now let's look at USB 2.0 data modeling in USB4 verification IP. It is backward compatible to USB 2.0, where the USB 2 traffic can be transferred over the Type-C interface that contains the DPDM lines. User can control the generation of USB 2.0 host in the USB 4 host router, number of USB 2.0 hubs, and number of USB 2.0 devices inside the USB 4 device router. USB 2 can run on all possible speeds. Number of endpoints can also be controlled, where it can go up to 31 endpoints. USB 4 dock functionality can be easily tested when the USB 2 devices gets attached to USB 2 hub present inside the USB 4 hub, where the XCCI controller is receiving the data via PCI tunneling. It is also possible to run USB 2 along with USB 4, where it can tunnel the USB 3 traffic as well. Next comes the USB 4 monitor and scoreboard. TrueChip USB4 verification monitor is easy to be plugged in an environment and is compliant to their standard respective specification. We have separate monitors stack for logical layer, transport layer, configuration layer, and protocol adapter layer. For DP, PCI, and USB 3. We have TMU monitor also. User can control the enabling and disabling of individual monitors in a simulation. TrueChip also has USB Type-C and PD verification IP monitors also. Along with that, we have monitors for PCI, DP, and USB VIP as well that can also be enabled and will be provided. Monitors will flash an error if there is a protocol violation with the ability to log this information. These errors can be easily masked and auto masking is also there. These monitors helps in coverage collection as well. TrueChip VIP scoreboard makes the design verification stronger by verifying packets type, header, payload integrity, and their count on all transmitting and receiving points. The scoreboard samples the packet from individual layer and from the monitor of each layer, then it traces and checks the integrity of the packet thoroughly throughout the topology. If there is any mismatch in the packets, it will flash an error. It summarizes the status of the checks and final count of each packet in the simulation. Let's look at few of the challenges faced to verify USB4. USB4 is an amalgamation of various protocols like USB 3, PCI, DP, Thunderbolt, Type-C, and power delivery. Testing of these protocols and verifying them with respect to USB4 is a difficult achievement. Verification of individual components and functionalities in a router has to be completed. For example, a host system has a connection manager, configuration layer, host interface adapter layer, multiple PCI, DP, USB 3 protocol adapters, a transport layer, multiple lane adapters having identical SerDes, a TMU block. So verifying these components alone is a big task. USB-IF also provides test matrix which needs to be fulfilled for a silicon or an USB end product depending upon the router type. CTS has various test cases to complete closure of USB4 verification, and these test cases repeats with various test setups, speeds, and also RSFSC and lane bonding can be individually enabled. It becomes difficult to maintain the skew between lane adapters, especially when RSFSC is enabled along with lane bonding. So these lane adapters tends to lose data or becomes out of sync with transport layer if special mechanisms are not allowed. There can be number of hub routers, divide routers connected at various depths from the host router at depth 0. So these routers domain can also be connected over other routers in a different domain. So one must test various domains and combinations of the topology. Native protocols like PCI DP has their own requirement to fulfill for bandwidth. So it's a challenge when a router is tunneling all types of traffic. Connection manager has to intelligently allocate the bandwidth to various adapters and also to avoid any overflow or underflow of the buffers. To avoid any loss of data or whether data integrity is maintained, TrueChip VIP scoreboard overlooks for these mistakes. It also checks for the correct packet routing. So there can be multiple other challenges as well, but one must verify the silicon or the end product thoroughly to avoid any problems during releases and tape outs. Now we will proceed how to inject error in USB4 verification IP. Currently, VIP supports two methods. One is using UVM callbacks and other using configurations to inject errors, like to override any configuration, timing parameters, etc. This is supported by all BFMs and monitors. Let's look at UVM callbacks. Callbacks are very important as it provides configurable access to each BFM or monitor without modifying the existing functionality or code so that the user can take control in their own hands like from the test case itself. It helps to increase coverage, generate unexpected scenarios, and also test the design at threshold limits. It's very easy to use TrueChip VIP callbacks. Just use this class in the test case and this will provide access to BFMs and monitors. For example, in the connection manager, one can override read request packet data or write request packet data, override route string, etc. Example for logical layer is also shown here, like to override RSVC block, sideband transaction data, overriding TS1, TS2, SLOS contents, etc. This is one example where HEC single bit error injection is done at the host router in transport layer. Overriding of ECC, ingress and egress adapter values in the routing table are also possible. Listed examples are for configuration layer like overriding 32 value and protocol adapter layer through which overriding of tunnel packets can also be done using callbacks. Other layers like TMU block or having control when inter-domain is enabled, this is also possible using callbacks. Now let's look at the second method, that is the configuration method. In this method, the configuration of any BFM or monitor can be modified at real time. One example is shown here where the mod configuration has been enabled at end of elaboration phase, where the read addressed RT transaction command payload has been modified to contain more than 2 data symbols, which should not occur according to the specification. The modification will happen at the host sideband channel. User can configure the timings, values on which address RT command the modification should happen, etc. Toggling of the configuration for all the test cases or individual test case or whether this should happen only once can also be controlled. Next, we will show the coverage summary. The image shows here the coverage summary for the USB4 environment and various BFM monitors. You can see here this is the top bus env. Different agents for the various monitors are also shown here for the host monitor agent, device monitor agent. We have also separate coverage for 5 monitor, transport monitor, config monitor, TMU monitor, and can be for protocol adapter monitor as well. This here shows that how many bins were hit and how many coverage do we have. Currently, we have 100% coverage. User User can also check sideband channel coverage summary. One example is shown here for sideband channel, but they can also open separate coverages for individual monitors. Here, the sideband coverage, it shows various cover points for LSC symbol, command type like ATRT, sideband channel state, which are idle, DLE1, LT, ATRT, DLE2. So how many times these bins were hit and how many transitions has happened. So we have bins for selected gen, whether the both Gen 2 and Gen 3 is enabled or RSFSE is there or all the TXFFE possible TXFFE parameters have been checked. Now let's look at the USB4 verification IP test suites. The USB4 verification IP test suite is broadly classified into basic and directed test suite, where it contains the basic and directed test cases for the protocol checking. We have the random test suite where it contains randomized test cases where corner scenarios can be checked and the sequences are randomized at fully. We have the error test suite where we deliberately inject the error using callback mechanisms or configuration methods. We have the compliance test suite, which is the CTS of USB4 provided by USB4 USB-IF. We have the assertion and cover point test suite. This will help to cover all the cover points and assertions. We have the user test suite as well, where the user can write own test cases by extending the sequences, or user can also write new sequences corresponding to the test case. Let's look at the number of test cases we have. For logical layer, we have 185 total test cases. This covers whole compliance test suite, functionality, and error injection test case. We have classified them in these categories. For RSFSE, we have 122 test cases For transport layer, we have 70 test cases. For configuration layer, we have 2 to 1 test cases. We have test case for host interface adapter layer and specific to connection manager as well, which totals up to 16. We have test cases for TMU and DROM, that is 29 test cases. We have test cases for all the 3 tunneling that is supported, USB 3, DP and PCI. So here are the counts of number of test cases respectively. Next, we have inter-domain test cases as well. To check the Thunderbolt interoperability, we have 32 test cases that will test USB 3 tunneling, DP tunneling, analog only, and PCI tunneling as well. We have low power test cases with USB 3, with PCI, with DP, and with USB 4 as well. We have 17 test cases. We have test cases to check the USB4 dock functionality. That is, the XSCI controller is present inside the USB4 hub and receives the data using PCI tunneling when Thunderbolt mode is enabled. So the first one, 7, shows the test cases for USB 3 data transfer, and second one shows for USB 2 data transfer. Here shows the total number of assertions on the USB4 pipe interface. We have 39 assertions for that. And here we have a table for number of monitor checks that goes up to 749, which is a very huge number. We have checks for in logical monitor, transport monitor, configuration monitor, TMU monitor, and protocol adapter monitor as well. Except these, the monitors for PCI, VIP, USB, DP are running separately. That goes up to a very huge amount of number. TrueChip VIP has various features that helps the user to perform seamless debugging, and the process is user friendly. Let's look at few of the processes. The TrueEye GUI is the TrueChip proprietary software that helps in automated integration, provides ease of debugging, running regressions, and etc. can be done with the help of TrueEye. Let's look at one example where the transactions performed in a logical layer sideband channel are shown. One can see the transactions done by host device with the timestamps. It also has transaction type, that is whether the possible AT, broadcast RT commands or the responses are sent. One can see the details of those particular transactions here as well. Here, the transactions of the logical layer lane adapters are shown as the TS2 and transport layer packets are seen. So one is performing training and other has reached the lane, the CL0 state. Here it can see that the lane 1 is performing these transactions by the host or the device. One can also see the descrambler seed and payload data as well. Similarly, for each layer, these transactions can be seen by the user. Here is the example of a transport layer transactions. TrueChip VIP provides two methods to mask the errors. One is the parameter method and second is the file method. In the first method, the corresponding error ID is used and value of the new severity is provided. For example, the WA here means the error PAME001. This ID would be masked as UVM warning. The second method is when the error needs to be suppressed or severity ID needs to be changed for all the simulations. Just give the corresponding ID, current severity and the new severity and it would do so. And here the corresponding IDs are written into this file so that the errors would be suppressed for the simulation. Whenever the error warning is reported, the TrueEye would flash a red highlights as shown here on the particular transaction. This would help the user to identify the cause. For example, here the sample transaction response was not expected for the previous command. Monitor has discarded the response. Error ID is shown here. Number of error counts can be seen here at the bottom and the user can help this to hover between various IDs. Now, if the errors are masked with the help of the methods explained previously, the warning messages would be shown in the yellow highlights. Similarly, it can be done for the info message as well. Searching for a particular attribute can also be done in this transaction view by the user, and filters can also be applied. For example, if one has to search a particular credit grant packet with HEC value as FEC, so one can easily do so. The TrueEye also generates different pie charts or command timeline views or line graphs that are generated to look at the statistics of various transactions. Here in this command line of the sideband channel transactions are generated, so one can see here during the simulation. Another example is shown for lane adapter where the different order sets and transport layer data is shown. One can run regressions, test cases, and do integration as well with the help of TrueEye. Now look at another method that helps in the debugging process, that is the debugging interface, which can be generated for all blocks. Here, an example of sideband channel debugging interface is shown. One can easily use this to check the flow of the simulation. As you can see, it contains full information like when the timer is started or ended, the CRC values, sideband channel state machine information, and the lane initialization is at which phase, etc. can be checked. Another example is for logical layer debugging interface for the lane adapters. User can see the lane adapter states, uh, what type of data has been transmitted, whether it is the order set of the transport layer data. One can see the order set counts, scrambler or descrambler value. So these are the few features that can be provided in the debugging interface. These things only help to ease the debugging and helps to complete the verification faster. All the standard interface signals can also be seen here, like the type C interface is shown for the user. So the devices and host what the bus data has been transmitted, and the sideband channel data can also be seen. Next method is the simulation snapshot. This eliminates an unnecessary simulation time required to simulate a common steps present in every test case like the training or path setup. This is done through a snapshot mechanism of a common simulation part by just simulating it once and using it as a black box for every other test case. For example, here, when the path setup is completed, the simulation is saved and can be used for another test case. TrueChip VIP provides this feature to create a snapshot database while running test case for the first time. As you can see directly here that in this other test case which performs the bulk-in, the snapshot is loaded directly after the path has been enabled and the timestamp is the same which takes the path setup to complete. So this is very useful to save the simulation time. This is the last feature that we will explain here, that is the user analysis ports. The TrueChip VIP provides this to access the BFM data. Various packets that are generated by individual layer and collected by the individual layer can be reviewed by the user just using these TLM ports. These ports transactions are also logged. In this presentation, all the tools that are used to simulate and to show the waveform or the coverage are the property of Cadence Design Systems. Next, we will proceed to look at the demo of few test cases. Now, we will show the example of a USB 3 bulk-in tunneling test case. In the current environment of this test case, there is a USB 4 host router and a USB 4 device router. They will tunnel USB 3 traffic via USB 3 protocol adapters which are connected to internal USB 3 devices. As you can see, first USB 4 link has been established as lane adapters has reached CL0 state after performing training. After the connected device router is enumerated, connection manager then can establish a USB 3 downstream and upstream path after a buffer allocation router operation to allocate the credits. This means now the USB3 traffic can be channeled over established paths. After this, protocol adapters will help in performing the receiver detection to the connected internal USB3 device link layers over pipe interface. Now, the respective USB3 links, as you can see, has reached the U0 state from the polling state. Now, since the test case intention is to perform a bulk-in data transfer, the XSCI would enumerate the USB3 device by performing various functions like set address, BOS descriptor, get device descriptor, set configuration, etc. After that, the device is able to perform the bulk-in. Here, it shows the host protocol layer logs where it has sent an ACK packet with number of packet 4 to request 4 data packets from the device with maximum transfer length of 102 byte. After that, the device initiates bulk-in and sends the requested data packet as shown here of length 1024 bytes. It here shows that the data is successfully completed and transferred and the XSCI driver has acknowledged it. This completes the intention and flow of this test case with the host and device goes into the low power since there is no data left to transfer. This is the test case for DP tunneling with VGA. Here, the host router and device router has completed the link initialization by reaching CL0 state, and both routers have been enumerated successfully by the connection manager. Connection Manager has now established a DP path after performing the buffer allocation router operation. In this environment, it has a DPTX followed by a DP-in adapter in host router, then a DP-out adapter and DPRX at device side. Firstly, the DP-out adapter and DP-in adapter will do HPD packet handshake to execute the DP adapter initialization flow. It enables aux transaction to power on the DPRX. LTTPR recognition begins here, where the DPTX perform an aux read from the LT-tunable file repeater DPCD capability and ID field to discover the presence, count, and capabilities of any downstream LTTPR. DPRX capabilities read and sync count read begins here at this sequence. This process enables the connection manager to know when to read the modified capabilities and recalculate the maximum bandwidth that may be consumed by this DP link. DPTX performs the sync count read to analyze the number of sync devices to which the DPRX is connected to. Now, setting of the link configurations begins here, where the lane count and lane bandwidth is set on which the data transmission occurs. The DPTX then proceeds with the main link training operation. This training can be performed in two ways, where the DPTX managed sequential link training or the autonomous concurrent link training, which is used in this test case. In this sequence, based on the DPRX capabilities, the training pattern is set in the DPCD for clock recovery. Here, sequences are running to indicate the setting of TPS1, that is training pattern sequence 1. When the clock is recovered correctly, it proceeds for setting the TPS4, training sequence pattern 4. After the clock recovery and channel equalization is successful, the training pattern set register in the DPCD is reset. This concludes the link training operation. Now, DP-in and DP-out adapters can tunnel the main and aux traffic. These tunneling packets can be of two types, SST and MST tunneling packets. In this case, we are doing with SST mode. This sequence generates the data for configured video format as shown on the screen with different values of hsync, vsync, hstart, restart, refresh rate, etc. These attributes are the attributes of the video format. These values are smaller than the actual values to fasten the simulation. The end of this sequence signifies that the video data is transmitted to the DPTX. Now we will wait till the DPRX receives the same video data through DP adapters. The following display indicates that the reception of video data by DPRX. It is one scan line at a time, one horizontal active pixel line at a time. Total number of lines is equal to the V active. The following display indicates that the number of video frame received, since this test is configured to send only one single frame. The end of the sequence indicates that the reception of all video data is successful and the test ends. It also has two scoreboard summaries in the end. The first scoreboard summaries shows the number of overall aux transactions, secondary data packet, and video frames transmitted and received in each component. The next slide shows the second scoreboard summary. Here, the number of external and internal aux transactions are shown with each adapter. This concludes the DP tunneling with VGA Testcase. TrueChip VIP supports the three low power states CL2, CL1 and CL0S. This test case holds the intention to test the successful entry and exit process into the CL2 state. The test case has been run on Gen 3 with lane bonding on and RSFSE encoding enabled configuration. It has one host, one hub and two USB4 devices connected. The lane adapters in the host, hub, and device routers will reach CL0 state after successful training and lane bonding. For a better understanding, we shall look at how the entry and exit flow to and from the low power state takes place between the host DFP and hub UFP link. For each port, we have separate debug logs for lane 0 and lane 1 adapters. For a reference, we'll be looking at the debug logs for lane adapters at both sides of the link. The upper side shows the hub lane 0 adapter logs and the down side shows the hub downstream port adapter logs. Objections for entry to CL2 state gets deasserted on the hub UFP and it starts to transmit the CL2 request audit sets. On the other side of the link, that is the host DFP, receives the request audit set and decides to reject the request by sending NAC audit set since an objection to entry to any low power state is asserted. Furthermore, upon the reception of NAC audit set, the hub UFP stops sending the request audit set and shall wait for some time before retrying. Meanwhile, when the objection to entry to CL state now gets deasserted at the host DFP, it starts to request entry to CL2 state by sending request audit set as shown on the screen. This time, the hub UFP accepts the request by responding with the ACK audit set since the objection was already deasserted. Upon reception of the ACK audit set, the host stops sending the request audit set and sends CL of audit set before it enters the CL2 state. The hub UFP moves to the CL2 state once it completes transmitting ACK audit set. While both the hub and host remain in CL2 state, the transmitter shall remain in electrical idle as shown in the down. The receiver also shall remain off. While the host DFP is in CL2 state, now suppose the objection got asserted in the host, so the host will initiate exit from the state by sending LFPS cycles. As soon as the hub detects the two LFPS cycle, it responds back with LFPS cycles. The receivers of both the link partners are enabled for bit and symbol log synchronization after LFPS cycle is received. After that, the lane adapters will retrain themselves and move to the CL0 state, thereby completing the exit process. A similar entry-exit process takes place for the other links also, for example, at the hub and the device side. Thank you. Let's look at another test case. This test case shows the functionality of a USB4 dock where there is a USB4 host, one USB4 hub in which USB 3.2 hub is present, and two USB 3 devices are connected directly to that USB4 hub, and there are two devices as well. Here, the PCI switch is used between PCI root complex and the PCI endpoint present inside the USB4 hub. PCI root complex takes data from the XSCI driver, which drives the sequences. PCI endpoint, on the other case, is connected to the XSC controller or the XSCI root hub port where the USB 3.2 hub is connected. After the links has reached CL0 state and connection manager has established a path. So firstly, all bar registers of PCI endpoints and memory base and limit registers of switch ports are enumerated. Here, the prefetchable and non-prefetchables addresses are also shown. After the PCI root complex and endpoint has established a connection, the 64-bar address is generated from PCI and is provided to the XSCI to generate its base capability, operational, runtime, and doorbell register addresses. The XSCI registers are flexible and can be altered in order to avoid the overlapping with the memory registers of PCI. After that, the host and devices would do the link training in USB 3. Here, the XSCI driver logs are shown in which the XSCI initialization is performed, which comprises of HC capability and HC params 1, 2, and 3. The XSCI can work on both 32-bit and 64-bit configurations. The XSCI initialization comprises of doorbell and other base addresses read operation from XSC controller. The wait interrupt is used in XSCI and can be performed either by the IMAN register or by sending the MSI signal from the XSC. There are two ports in XSC controller, so our VIP is flexible to connect the hub on either of the two ports. After the XSCI initialization is done, hub enumeration is started with the set address command. Hub enumeration can be done with full or minimum required flow. Full flow comprises of set address, get device descriptor, get boss, get config, set config, get hub descriptor, etc. In the set address, host provides the address to the hub through this command. After the hub address has been set, the input slot and endpoint control contexts are written. Here, the XSC driver supports the device speed up to 5. And output slot and endpoint contexts are read here. After that, we will proceed to the get device descriptor where the device capabilities and number of configurations are read in this command. Here, the command is generated to perform the get device descriptor. Now, we will proceed to the get boss descriptor. This is an optional command which helps to read extended capabilities of the device. The get configuration descriptor command reads the endpoint with interface information of the device. After reading the descriptors, the set config command is used to set a particular configuration in the environment. To read the capabilities of hub, the get descriptor command is used here. After the hub initialization, the set hub depth command is used to determine the route string of the hub so that the packets can be seamlessly transferred to the hub. After that, the hub interrupt sequence is executed on interrupt endpoint of hub to read the information of ports valid to the connected devices. The VIP is capable to connect devices on any port number. For example, if we have 8 downstream ports in hub, so we can connect the device on port ID 3, 5 instead of starting from 1 or 2, that is doing it sequentially. This here shows the link layer logs of the host where the interrupted data is read. That is here the 6 and the 0 are the data payload, which means that two devices are connected on port ID 1, 2. Then status change byte is updated according to the enabled port IDs where the devices are connected. After that, the XSC driver would perform the get port status where it would get the status of the ports to check the port power connect status where the port link state to judge whether the device is USB 2 or USB 3 device and is successfully connected or not. Here we can see that the W index is 1 which signifies port ID. After completion of the successful port status and the devices are connected successfully, the desired slots are enabled by enable slot command sequence. After that, the enumeration of the first device is started, which is this doing the set address, get device descriptor, get boss, get config, and set config sequences. All the commands are same as of hub, but now slot ID is incremented to 2 and the route string follows the port ID to which the devices are connected. After performing the successful enumeration of the first device, the second device is enumerated with the same flow, but the slot ID here is 3. After the enumeration of the second device is completed, the bulk transfer has been initiated from the XSC by sending an ACK packet. Here it shows the transfer is completed for the first device. After the bulk transfer initiated for the second device. This completes the intention of the test case where the USB 3 data transfer occurred using PCI tunneling for the XSCI data where the two devices are connected directly with the 3.2 hub present in USB4 hub. Thank you. Let's look at the deliverables provided in USB4 verification IP. In USB4 verification IP, USB4 host, device, and hub can be provided along with retimer as well. USB4 BFM agents for connection manager, electrical layer, logical layer, and all types of layers will be provided. There would be a layered monitor and a scoreboard as well. All the test suits explained previously, which are basic and directed, low power, error scenarios, stress testing, compliance test suite will be provided along with TrueEye GUI analyzer. All the other VIPs for PCI, DP, Type-C and power delivery will also be included. Along with that, the documents would include the release notes, the quick start guide that will help the perform the integration faster, a user manual which contains all the configurations related to each layer, the integration guide to set up the various topologies to integrate the DUT, whether it's a hub, whether it's a retimer or a device or a host, it doesn't matter. DUT specific integration PPTs are also there. Test plan with test case description with test case flow. So all the test cases, what test case flow is intended by the test case is also described. Number of test cases for individual layer is also there. Regression list specific to DUT and all the features and the test cases are also included. There would be a TrueEye GUI usage guide as well. This concludes the presentation. I hope you will consider TrueChip as your preferred VIP partner. Thank you from my side.